Okay, so 12E is multi-stage experiments and the product rule. So let's read through the theory. We're doing two-stage experiments. If A and B are events in successive independent stages of a two-stage experiment, then the probability of A then B is the probability of A times the probability of B, where the word independent means that the outcome of one stage does not affect the probability of the other stage, okay, because they're completely independent events. So there's more here on independent events. The word independent needs further discussion. In the example above, the throwing of a die clearly does not affect the tossing of a coin, so the two events are independent. Here is a very common and important type of experiment where the two stages are not independent. So here, this is the example. Choose an elector at random from the New South Wales population. First note the elector's gender and then ask the elector if he or she voted Labor or non-Labor in the last state election. So obviously there is an option there for an overlap. In this example, one might suspect that the gender and the political opinion of a person may not be independent and that there is a correlation between them. This is often the case, as many opinion polls have shown over the years, and we will be doing more work on independent events in Year 12. So for multi-stage experiments, we talked about two-stage experiments, multi-stage meaning as many as we want. If A1, A2, ... meaning as many as we like all the way up to AN, are the events in successive independent stages of a multi-stage experiment, then the probability of A1, A2, all the way up to AN, you multiply those probabilities together. Probability of A1 probability times probability of A2 times all the way up to probability of AN. Okay, so let's try some questions. Number 1, a pair of die are thrown. What is the chance that the first throw gives a sum of at least 5 and the second throw is a double? So our notation is actually going to be helpful in a lot of cases in this exercise because there's actually going to be a number of different outcomes that you could use. So I'm going to use some labels in here. I'm going to use probability of at least a 5 and then a double. Okay, I've got a comma separating the two events. The first one is we want at least a 5 and the second one is that we want a double. Now this is referring to throwing two die, and we've seen in previous exercises that it can be very helpful to draw up a little table showing the outcomes. You may get to the point, or I hope you get to the point, where you're so familiar with this table that you don't need to draw it up. Okay. So I'm not going to fill the whole thing in, but the first thing that I wanted was the probability of at least 5. Remember that the sums work on a diagonal. So I'm going to just tick the boxes that have 5 or more. So 4 and 1, 3 and 2. I was going to work down the diagonal. Anything bigger than that, anyone that's in there, they're all going to be bigger than 5. 3 and 2 makes 5, and any other ones down there are going to be bigger than 5. 2 and 3 makes 5, so all these ones underneath are going to be bigger. 1 and 4 makes 5, so those ones down there. And the 2 rows that I left on the end, all of those are going to be greater than 5, because 5 is the starting number. If I add anything on, it's going to be bigger than 5. So quite a lot of them. Let's count them up. 6, 12, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Guys, count 30? So there are 30 ways. That's our first number. 30 out of the 36 are going to give us a sum for at least 5. That's our first selection. Then we multiply the probability of our second selection, which is a double. So the doubles, I'll change colour. The doubles are the 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, which there are 6 of them out of the 36. And all we do is times those probabilities together. You guys get the answer?
1/75. What?
What did you get?
Answer to 36.
I got 5 out of 36.
How? Isn't there 6 numbers? So you have 6 doubles.
Let's type it in. Timesing those numbers together.
I
Thank you, good. You didn't get anything because you need a calculator.
Yes.
Right.
Cheers, miss.
Okay, yes. 30 over 36 times 6 out of 36.
How did I get one?
Okay.
5 out of 36.
Okay, all right, we're good. Question 2, let's keep moving. A coin is tossed 4 times. Find the probability that. Now, in a lot of the questions that you're going to do in this section, you can always draw a tree diagram. And that could be very helpful to see the outcomes. However, if we're tossing a coin 4 times, that's a very large tree and it will be quite time consuming. So if possible, if you can do it without a tree, you should be trying. You need to try and save that time. It's very precious in your exam and precious when completing your exercises. So, the first thing we want to find is if we toss 4 coins, we want to toss a head every time. So that means I want the probability of head, 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 head. 4 heads. Now every time you flip a coin, the probability of getting a head is a half. So that just translates to half times a half times a half times a half, which makes 1 out of 16. Part B, find the probability of no toss being a head. That means that I'm actually after tail, 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 because I want no heads. So that's going to be the exact same thing. It's a half times a half times a half times a half, 4 of them, which is again going to be 1 over 16. So part C, if it says there is at least 1 tail, that means I want everything except for the all heads. Okay, so probability of at least 1 tail is going to be 1 minus the probability of head, 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 because everything else is going to have at least 1 tail in it. And we've already worked out the probability of the 4 heads, which is 1 over 16, which means there's a 15 out of 16 chance of there being at least 1 head. All right. Question 3. A box contains 5 discs numbered 1, 2, 3, 4, and 5. 2 numbers are drawn in succession without replacement. What is the probability that 1 number is odd and 1 number is even? What are the possible outcomes that I could get that fit that criteria? There's 2 of them.
3 and 5.
Oh, yes, sorry, I'm not meaning that specific. I'm meaning the order of the odd and the even is not important. So the probabilities that I'm after is actually probability of odd then even plus the probability of even then odd. Okay, we just know we need 1 odd and 1 even, but it didn't tell me the order that they had to be in. Okay, so let's work out those probabilities. Odd then even, looking at my 5 numbers, there is 3 odd numbers out of the 5. If 1 odd number has been selected, I then have 4 numbers left to choose from, and I have to choose an even number. How many even numbers are there left out of the 4? 2. So I'm going to times that by 2 out of 4. That's the first probability. Then I want to add, these would be 2 separate branches on my tree if I was doing the tree diagram, which we're trying not to do because we want to save time. Probability of even then odd, back to my original 5 numbers, there is 2 even numbers out of the 5. 1 even number is selected, so I'm down to 4. How many odd numbers remain? 3. So it's 3 out of 4. for the second fraction there. Now, the good thing about those two things is they actually work out. If you times those together, you get the exact same thing as if you times those together. They are both equal to 3 out of 10. Okay? But it's important to recognise that there are two branches. So you'll have to double that 3 out of 10 to be 6 out of 10, which simplifies to be 3 out of 5. All right, one last question. A coin is tossed 4 times again. Find the probability that the first 3 coins are heads. Okay, so probability that the first 3 are heads. What are my options? The options are, I don't know what is happening with that 4th coin. It could be head, 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 head. Who knows? They could all fall. We don't know what that 4th one's going to be. Or it could be probability of head, 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 and tail. Both of those options for 4 tosses of a coin have the first 3 being heads and the last one is up in the air as to what. Doesn't matter what that last one is. Okay? So there's 2 branches. Each one of those branches, because it's back to a coin again, every time if I'm doing the head, 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 for example, it's half times half times half times half. So half times half times half times half. Now, if I'm going to do head, 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 tail, does that change anything for my numbers? No. It is still half times half times half times half. The key thing in this question is that the probability along those branches are all equal, but we need to know that there's actually 2 branches that fit our criteria. So when you times those together, you obviously get the 1 out of 16 that we got before, but because there's 2 of them, 2 out of 16, which simplifies to a 1 out of 8. Okay, part B. Draw a little line down here. We're going to need some working out room. The middle 2 coins are tails. So the first and the last could be anything. We need to list off all the different possibilities here. So probability, middle 2 are tails. Okay, what's the possibilities? Let's...
Faster to write 1 over 2 before.
Yeah, you could do that. Yep, sure. That's the same. Yep. Probability of tail, 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 tail. I could start with all 4 of them being tails. I'm going to keep those middle 2 tails and do all the changes around it. So then I could do probability of tail, 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 head, plus probability of head, tail, tail, head. Is there another one? Yes. Yes, probability of head, tail, tail, tail. Okay? Now, hopefully, we're recognizing now that each one of those probabilities is going to be a half times a half times a half times a half, or half to the power of 4. Okay? The idea is that you need to find that there are 4 branches that have that probability, and we're doing it without a tree. Okay? So it's going to be 1 over 16 plus 1 over 16, or you could just do 1 over 16 times 4. In other words, that's going to simplify to a quarter. So with this knowledge in mind, that each one of the branches on that tree is 1 over 16, we're going to use that knowledge to help us complete this table for flipping 4 coins and the different number of heads that is possible to get. So I'm going to do a little bit of working out down here just to show you how we're getting the answers. If I want the probability of no heads, that means that I want the probability of tail, 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 tail. Okay, we've done this enough time. Is that easy enough to say that's 1 over 16? Cool. Then, if I want 1 head, how many different possibilities are there? Well, that means that 3 of them have to be tails, and I have to put all the different places where the head could go. So it could be, the head could be first, so it could be head, tail, 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 Or I could move it down one, and it could be tail, head, tail, tail. Or it could be probability of tail, tail, head, tail. Or the probability of tail, 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 head. Can you see what I've done? I just moved the head down one spot each time, and we've identified that there are 4 branches that give me what I want. So it's going to be the 1 over 16. Each one of them has a 1 over 16, and I'm just going to times that by 4 because there's 4 branches that give me that. Okay, that makes a quarter for that next one.
Miss, why wouldn't it just be 1 minus 1 over 16?
Because that's just saying you want any number of heads, not just one head. Okay. All right, next option. 2 heads anywhere. Okay, how many different possibilities are there? This is going to be the most complicated one. So it could be the probability of head, head, tail, tail. Okay, I'm going to keep one of the heads in the first position. I'm going to move the second one. So it's going to be the probability of head, tail, head, tail, plus probability of head, tail, tail, head. Okay, so I've moved one of them all the way down to the end. But there's still more. Now let's move the first head down. So it could be probability of tail, head, head, tail, plus probability of tail, head, tail, head, plus probability of tail, tail, head, head. 1, 2, 3, 4, 5, 6. There is 6 of them. Do you see? If you do it in a systematic way, like I just did there, where you're just moving one head down the line, then you're moving the second one down so that you don't miss any of the possibilities. There are 6 different branches. So that is a 1 out of 16 chance for each one of the branches, and times that by 6, which means the probability of getting 2 heads is a 3 out of 8. And finally, 3 heads means that there's 1 tail that I need to move around in there. So it could be probability of head, 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 tail. I'm putting my tail on the end for a start. I'm going to move it up the line this time. Probability of head, head, tail, head. Plus probability of, I think you probably know where this is going, head, tail, head, head. And that means probability of tail, head, head, head. So maybe as we expected, we're back to having 4 branches there again. So 1 out of 16 times 4, and that means we're back to a quarter for that one. The last one, I'm pretty sure I don't need to write this one down. The probability of 4 heads.
1 out of 16.
1 out of 16.
Is there an algebraic version to work this out?
That could be fun.
Or a way that doesn't.
No, that's fine.
Is there a way that isn't?